we'll talk about group foliations of finite difference equations using equivariant moving frames.
First, thank you very much for inviting me. And so now I have, I think, a big shoes to fill after my PhD advisor was here 2 weeks ago, and everyone was saying like amazing talk and all that stuff. So we'll see how I can do. And so yes, I guess Peter came 2 or 3 weeks ago and talked about applications of moving frames. And I guess the plan today is to give another example, probably, of an application of moving frames. So what I want to do is explain how we can use moving frames to actually solve finite difference equations. So that's the goal. And then I guess, and so I think most people are more familiar with differential equations. So just like a small introduction. And so if we give ourselves a differential equation delta, we have this notion of symmetries of differential equations, which are more familiar. And so it's we give ourselves a Lie group G, and then we will say that this Lie group, which is allowed to act on the independent variable x and the dependent variable y. Okay, so we'll say that it forms a symmetry group if it sends solutions of our differential equations to new solutions of the differential equation. So that's the notion of symmetry. It preserves the set of solutions. And then another way of thinking about it is that if you take your group and you act on the equation, then the result will be the equation itself. So like you don't see the equation change under a group of transformation. And so that's a symmetry group. And so
K is the order?
Huh?
K.
K here, oh yeah, so here is the order of the differential equation. Yes, thank you very much. I should say if you have any questions, please ask. So here, yeah, so y superscript k will denote y, its first derivative, I mean all the first derivative, the second derivative, up to order k. So it collects all the derivatives together.
I have a question actually about your comment. What is the exact relation between G being a symmetry group, in your sense, and G preserving the equation?
Preserving the G being a symmetry group?
Yes, and you made a comment about preserving the equations, that it's an equation to itself. Could you clarify the precise relation between the definition and your comment?
Clarify, so...
Maybe could you repeat your comment? About
Sure, I can. Yes, I can do that. So you have or maybe if I give the example, we can that will make it easier if we look at the actual example. So here we have the first order ODE, like one of the simplest possible cases. Okay, so while it's not obvious, though, this differential equation is invariant under like rotation around the origin. So in other words, so if you were to replace x and y on the right-hand side by this transformation here, and then also compute how the first derivative transform under the chain rule, you would transform this equation, and when you apply the rotation, you would recover the original equation. So it takes this equation and then it sends it to exactly the same equation.
Think of the equation as a vector field, and if you have a...
Oh, but I wonder about the converse.
Oh, if it preserves that. Yeah.
Then it's not clear.
Yeah.
It could be different equations that...
Yeah.
So you could have many equations that have the same symmetry group. Yeah. Okay. Yes. So yeah, you could have two different equations that have exactly the same symmetry group. Like there are many equations, in fact, that have no symmetries, and so or other than the identity. So all the equations that have no symmetries, other than the identity, there are many like that. So it's not a one-to-one correspondence, and so. Yeah, so many equations might just have dilation, for example, and so.
Just look at this one where all the orbits are circles.
Yeah, so like here you can.
The same group.
So here, if you look at the solution space on the right-hand side, so we can solve this equation, and then now if you each curve corresponds to a solution, and I think the picture is nice. Now you see that if we start rotating the picture, it will send one curve onto the other. In other words, it will send one solution onto the other solution. And so there are other ODEs, at least, that will have solutions that will be invariant under rotation.
Fix this.
So does that answer the question?
Yes, thank you.
This is the first.
And then Sophus-Lee was the first one to observe that, in fact, when we teach how to solve ODEs to undergrads, like we say, oh, we have a first order linear ODE, here's how we solve it. You do the integration factor trick, and then say, oh, you have a homogeneous ODE, here's another trick. And so for undergrads, like it seems like this is just like this whole course on ODE is just like a course where you learn tricks and you don't really know why you're doing this. And then Sophus-Lee was in fact the first one to realize that all these different techniques, in fact, are just particular cases of what I would say like integrating differential equations using symmetry techniques. And so he's the one who introduced, I guess, this idea of using symmetries to solve differential equations. And so one of the techniques that he developed is now called, I guess, group foliation. It's also called group splitting also sometimes in the literature. And so that's a method for solving differential equations. And in one of his papers, he gave like 2 examples of what group foliation is, and then that was like published in 1895. But he just gave 2 examples, like he was talking about symmetries, and then he said, oh, by the way, we could actually solve these 2 equations that way. And then didn't mention much more about it. And so after that, it's more Visio who took the 2 examples and developed the rigorous theory of group foliation. So that was done in 1904. And so then after this, somehow nothing happened for about 65 years. But then the Russians came, and Zianikov and his colleagues started to apply this method of group foliation to partial differential equations from fluid dynamics. And so that's when I think also these symmetry techniques applied to differential equations became big again. And then somehow there was another little break between 1969 and the turn of the 21st century. After this, some people started applying the group foliation method to the Monge-Ampère equation and the Heavenly equation. And then recently in 2005 up to 2008, some people have started, like Jan Anderson, Mark Fels, and Juha Pohja-Pelto. They recasted the whole theory of group foliation using exterior differential systems, so in a coordinate-free fashion. And then in 2015, this group foliation technique for differential equation was also recast using the method of moving frames. Okay, so that's I would say the history of the method of group foliation for differential equations. And now today, in fact, that's not what we want to talk about, but we want to talk about how could we use this method of group foliation to solve finite difference equations. So that's what we will, at least that's what I would like to talk about. So, yes. So we will see how that works. So that's my goal for today. And so to make the talk as simple as possible, I'll restrict myself to the simplest case possible. So we'll look at, say, instead of looking at, say, ODEs, where the solution is a curve in the plane, say, what we will do is we will not look at curves anymore, but we'll look at points in the plane. So we can think of taking a curve in the plane and sampling that curve at various points. And then we'll denote these points by Z subscript n. So n will keep track of the sampling, and so here, so we will consider a space, the collection of all points in the plane which are denoted by Zn, where the coordinates are given by Xn and Yn, and then the integer n can take integer values. Okay, so that's what we're looking at. So we allow ourselves maybe to have infinitely many of these points. And then for convenience, we will do the following. So we'll introduce the kth order forward discrete jet at an index n. And so the notation will be this one here, so it will be z subscript n superscript k, and it's just a way to collect points together, so it will be the point zn plus 1 up to zn plus k. Okay? And why is it called the discrete jet? It's because this is the minimum number of points that one would need if one wanted to approximate the function y, its first derivative, and its second derivative up to order k. Okay, so like if we, in differential geometry, this would be called the kth jet of a function y, and now in the discrete case, we'll have kind of the same analog, but it will, so it will just be the collection of these points together. And if we have these points, technically, we can approximate derivatives. Then we'll collect all these discrete jets together, and so we'll take a union over all the indices n, and then we'll call the result the forward discrete jet space. So it's kind of the approximation of the of the jet space in differential geometry. And then once we have this, we can define what a difference equation is. So it will be essentially, so a difference equation is just an equation which will relate a kth order discrete jet, then nk, and maybe the function can also depend on n. Okay? And then just for convenience, in the next formulas, like instead of writing the dependency of n explicitly, I'll put n as a subscript. So if you see e subscript n, it just means that the function e can depend on the index n. Okay? And so a difference equation will be a relation between the points zn plus 1, zn plus 2, up to zn plus k. Okay? And so these finite difference equations are used obviously in numerical analysis, and they're frequently used to approximate differential equations. And so that's one of the...
What kind of function is E sub n?
E sub n, so it's a... so this would be,
Polynomial or?
anything. Like I don't have like any restrictions on E.
Okay.
So it's just a relation between neighboring points. So like, just like, yes. So just a way to relate neighboring points together. So it does not have to be polynomial, it can be anything. And so an example of I guess, is the following one. So here we have say a first order ODE, and it can actually be approximated by two equations. So here on the left we have this big equation here. So this is what this would be an example of the equation E. So this relates, let's say, the point xn, yn, and the neighboring point xn plus 1 and yn plus 1. Okay? And it's not obvious, but as the point xn, yn gets, I guess I should have said it like that. So as xn plus 1, yn plus 1 approaches xn, yn, so as they get closer and closer, this in the limit will actually converge to the differential equation. So it's not obvious, but that's the case.
So you didn't mean 1 minus b, did you?
Huh?
You did not mean 1 minus b, right?
Here?
The exponent here, is it indeed?
Yeah, it's 1 minus b.
Really?
Yeah. Is that?
Okay. How did you get that? I'm just wondering.
Yeah, so it's true that it's not obvious how to, so this, how did I get that? One way of answering this, like if you have a differential equation, obviously there are many ways to approximate the equation, so this one is not very obvious. Like this would not be if I were to ask anyone to find a discretization of this ODE, no one would write this, I'm pretty sure. Everyone would just take probably like a standard forward Euler approximation for the first derivative, and then this would just be approximated by the same expression evaluated at xn, yn. So I agree, it's not obvious, but then in this talk, we want to have symmetries all included inside the finite difference equations. And so this equation here will actually admits a one parameter symmetry group. And we want to approximate the equation in a way which will actually also preserve the symmetries. And so that's where it becomes complicated. The standard approximations will not preserve usually the symmetries of the differential equation. And so now that's like a whole talk about how to actually construct these finite difference equations that actually preserve the symmetries, but somehow this could be done. So for now, I think we would need to hopefully believe that if we look at the continuous limit as the points get closer and closer, this will converge to that expression. So one can take the Taylor series expansion of yn plus 1.
Even for b equals 1.
Oh no, so it's true that it's not written on my slide, so maybe I need to probably say there are two restrictions. Obviously, we can never divide by 0, and so even here, I didn't write it, but b should not be equal to 1, and a cannot be equal to minus 1. Okay? So yes, so it's not written, but there are these two restrictions.
But if you multiply all out by denominators, if you clear denominators,
Yes.
at b equals 1, does it still make sense?
What do you multiply by 0?
Well, okay, so you can rewrite this. Just first clear denominators.
So yeah, so if b equals 1, at least one thing I can say, at least so the thing is that if b is not equal, so if b equals 1, this ODE will now have also, I could mention, will have a symmetry which is given by dilation. So like if you dilate y by a scalar lambda, and this equation will remain unchanged. And so if you allow b to be 1, then your symmetry group will, in this problem, would be bigger. If you don't allow b to be 1, it like decrease the number of symmetries. And so, yes, you could, but this scheme would not work. So because like the way it's written now, I guess. No. So that these schemes assume that b is not equal to 1. Sure.
So suppose I take k equals 0, a equals 0, and b equals 0.
Yes, we could do that.
Okay, so that right-hand side would be just 1, right?
Okay.
Everything
Yes.
0.
Yes, everything. Yes.
Everything 0.
Mm-hmm.
Now, why is that in the equation then? So the k term times xn plus 1 minus xn is gone, right?
Yes.
In the equation,
Mhm.
all right? And then what you have on the x coordinate,
So we have this.
that would be just x of n plus 1 minus x of n
Yes.
divided by 1, right?
We'll have
And the
so
same
we'll have x n plus 1, and then we'll
minus
have
xn.
plus y
Okay, all right.
n plus
We
1.
do that.
All right.
Divide by 1, right?
Oh yeah, everything will.
I think
No, this
minus.
is divided by minus. This is because it's divided.
okay.
Now it's b minus 1.
Okay.
Again, then after that we'll have plus x n. Minus, about that, minus, and then x
Xn
n,
minus
and
y.
minus y n, and then this is equal to 0,
Right,
like
okay.
this. And now we
This
can,
is why-
So,
and then we will,
move the x terms around.
yeah, so let's move the x terms on the other side. So we'll have a minus y n plus 1 plus y n equals negative x n plus 1 plus x n. Like this. And then we can divide by this by the right hand side, and then it will give us negative y n plus 1 plus y n divided by negative x n plus 1 minus plus x n, that is equal to 1. And then but then usually I guess I would rewrite the left hand side as y n plus 1 minus y n divided by xn plus 1 minus xn, and this is equal to 1. And so this is the usual first order approximation for the
Right.
dy dx.
Now, my question is, what happened to h?
To h?
Yeah, you said x and y, so you see.
No, yeah, so I haven't had the
H is
time to
step
talk
size, right?
about this equation
See,
yet.
H
So
is
this
the
will
step
be
size.
now this, so this
H
will
is the
be,
step size, right?
yes, yes.
But when
yes.
k equals 0, the equation that you have has nothing to do with h, or almost nothing.
No, it has nothing to do with H.
Well, how can it be not?
But it has to, like, it has to, it is,
How can you be discretizing and not using the step size?
but it is somehow, oh, I mean, the way now that it's written here, like, if say k is not here,
Yeah.
but there's still an xn plus 1
Yeah.
here, and so if I really wanted, I could use this equation and replace everywhere I have xn plus
right,
1 by
xn plus
xn plus h, and then the h would be included into
But
it. Yes.
it's actually here.
Okay, so
It's actually, yes, so now, if we had, yes, so I could replace this by h, yes. The thing is that when you look at finite difference equations, you don't want to restrict yourself to like equations where the step size will be constant, because that limits the type of symmetries that we can actually consider. So usually what we will do is we will have, if we're trying to approximate, let's say an ODE, like in this example, we'll have one equation which will be an approximation of the ODE, which we have here, and then we will add an extra equation that will specify the mesh, and we will give ourselves enough liberty for, let's say,
So
the step size.
why don't you call it h sub n?
X sub n?
H sub n. H sub n.
Oh yeah, the thing is that, yeah, okay, so here in this example, we can take the step size to be constant. Yeah, so for this problem. But in general, you'd want it to be a function. And also, the step size could technically depend on the solution. Yeah,
Okay.
that's also a possibility. And so, yes. And then you wouldn't want probably, like if you, to have the step size depend on the behavior of the function, like the steeper the function is, the smaller you might want to have your step size to have a better numerical accuracy and things of that form.
And could you say again, so that approximation, it was a result of applying some algorithm?
Yes, this is correct. So I took this equation from like a paper from Pavel Winternitz, and so he was one of the first to look at this problem of how can we discretize a differential equation in such a way as to preserve the symmetry of the differential equation. And so he introduced an algorithm for doing that. And so, yes, so it's very algorithmic, and so that can be done, yes.
You mentioned that this equation has symmetry.
Yes.
Can it be seen by naked eye, or is something complicated? Because I look at the equation and don't see the symmetry. Is it? Should it be?
No,
obvious?
it's not obvious, but I'll
okay,
give
so
it
we'll
to
see
you.
it later. Okay.
Yes, I will. Yes, it's by. I mean, if you, it's here. So, it is, so far we've done like in this talk. My goal would be hopefully to solve this equation explicitly. Okay.
Okay. Then we'll
And
see.
so
Okay.
this equation has one symmetry, and it's not obvious, but it's given by this thing.
Okay.
This
Okay.
formula
Thank you.
Here. It's you can see obviously that the second equation here is invariant under the claim translation in x. Like so, if you translate xn by epsilon and translate xn plus 1 by epsilon, then the epsilons will cancel in that formula. So I think for this equation it's obvious. It's less obvious for the other one.
And this type of discretization, is it now typical numerical analysis, or it's something new for numerical analysis?
Yeah, I would say it's something newer, I guess. New, yes, yes.
So
It's been around for, I would say, 10, 15 years-ish, but it has not been like used very much, and I have reasons to understand why. Though it's the problem of the people that are involved in the field. So like the people that have been studying symmetries of finite difference equations have never been really interested in the numerical analysis, like the numerical parts of it. No, but maybe I'm wrong in saying that, but like people have been more interested in like the theoretical aspect of how do I preserve the symmetries, but very few people have asked themselves like, are these actually good numerical schemes? Okay, so like a lot of people have been focusing on let's construct these schemes. What are the algorithm? What are the steps that that if I take a differential equation, I go through the step, at the end I have a numerical scheme that preserves those symmetries. Once they had the scheme, they were happy. They would move on to another problem. No one really has spent time asking, are these schemes actually good? And in many cases, the answer is no. And so now there are more and more people, there are like younger people that are actually saying, yeah, okay, we can preserve these symmetries, but there are many ways of preserving these symmetries. We also need to do this in a clever fashion. And now there are like people are working and developing new symmetry preserving schemes that actually give good numerical results. Yes. So it's like eventually it will get to a point where it might attract more attention from the numerical analysis community. That's for sure. Yeah, so like, I mean, there were some examples that were published of like preserving the symmetries of the heat equation. And so people would write down a numerical scheme and then would just say, oh, this scheme preserves they preserve the symmetries. But then if you wanted to implement it, the scheme would start like the grid would try to start like crossing each other. And so like it could not be implemented. And so some people are now looking at ways to avoid the like crossing of the grids and these issues, which can be dealt with. At first, people didn't care about that. Yes, and so here, like, why do we care about finite difference equations? Well, obviously, they're used in numerical modeling. They also appear in discrete quantum mechanics and also in discrete general relativity. So as a way to try to combine quantum mechanics and general relativity. It also appears in discrete time economics and also in chaos, things like that. And so I guess today, when we will consider a finite difference equations, we will assume that this equation has a symmetry group, okay? And so we will say that a Lie group G is a symmetry of the finite difference equation if it sends solutions to solutions, just like it did for differential equations. And also another way of saying that is that if you act with your symmetry group on the finite difference equation, it has to give you back the equation you started with, just like for ODE. And then when I say act, what do I mean? So how does the Lie group act on a finite difference equation? The answer is that it acts by the product action. And so if you give yourself an element G inside the group, then it can act on Zn plus 1 up to Zn plus k. And the action is given by the same action on each point.
So so the previous thing that you just mentioned, that's what I don't understand. You said that it has to give you the equation back.
Yes.
So is this a definition or is this a theorem?
That is I would say
It's not equivalent to preserving solutions, is it?
I would say it is the same thing. So if it sends the equation onto so like if it sends one solution to a solution, then these two solutions will satisfy the same equation.
But the set of equations that the solutions satisfy could be different equations.
Different with the same solutions, you mean?
Yeah. Yes.
So two different equations would have the same. So two different equations would have the same solution space.
Yes. So why not?
So I guess
that's what I don't understand. We're saying it has to, it has to get back the same equation. That's what I did not understand. Why you said that. Or I guess I don't understand the definition again. So it is. So that's the definition.
Yeah, so if you're given an equation. So this you have the equation, and then the symmetry group of that equation. The definition would be the following. So you're given the equation E, and then G would be the symmetry group if it sends the solutions to solutions. That would be the original definition of a symmetry group.
So you don't mention anything about the equation, preserving the equation. You're not claiming that.
But it does. As a consequence, like it will
But I
send.
mean, it doesn't exclude other ones from having the same solutions, I think is what maybe a misunderstanding.
Right.
Like, if it preserves the equation, then it will map solution to solution. So
Right, but not the other way.
No, not the other way. Not necessarily.
Not necessarily the other way.
Yeah.
Okay.
So the original definition is that will be the first one. So it will send solutions to solution, and as a consequence, it will send the equation onto itself.
That consequence I don't understand.
Let's just move.
Okay, let's move on.
Okay.
We'll talk later.
And so, so an example is like if we look at this finite difference equation, this is always the one you will be seeing in the whole talk. So here we have our finite difference. We have two finite difference equations, and then the claim is that these two equations admit a one parameter symmetry group, and it's given by this. So there's this epsilon here. That's our group parameter, and so if we start translating x by epsilon. Okay. And then the transformation rule for y is more complicated, but it's given by this formula here. And the equation will remain unchanged under this expression.
Do you solve over reals?
Huh?
Do you leave over reals? Because like you'll need to extract root of degree 1 minus b.
Yeah, but the thing is that the equation is already like technically like we could almost make a change of variable. It's like this fraction y to the n, like y to the 1 minus b over b minus 1
will
appears
be
here,
separate
it
variable.
appears here. And so now the way like this expression is written inside, so this fraction here now, if you ask yourself, how does this fraction, how does this fraction transform now? Then the answer is that this thing here, so in capital letters means like how, like the image of a transformation. So this ratio here, if you act with the group, it will transform according to this formula here.
Okay.
That's what it means. And so if we were to take this formula, substitute that inside, and then simplify, everything that involves epsilon would cancel, and then we would recover the equation we started with. So it is a symmetry group.
Okay. Thank you.
And so our goal for today is, given a finite difference equation or like a system of finite difference equation that admits a symmetry group, we would like to use the group to solve the equation. Okay, and so that's our goal. And so here in this picture, we have, say, an equation E equals 0, a finite difference equation, and then what we're trying to do is we're trying to find a discrete solution to that equation. Okay? So we will do that using the group foliation method, and I just wanted to give you an outline of how this will work. And so the idea is the following one. So we will not try to solve the equation that we start with. What we will do is we will somehow project the solution space of that equation onto the space of invariance. Okay, so we'll do like this projection. And then what we will do is we will try to solve the problem in the space of invariance. Okay, so here we will try to find the solution in the space of invariance. And why do we do this? Typically, this problem will be easier to solve than the original one. Okay? And then, if we're able to solve the problem in the space of invariance, then the last step will be somehow to take this solution and recover the original solution through like what we call the reconstruction step. Okay? So we will take the solution here and reconstruct the solution, the original solution. And so if we're able to do that, then we'll have the solution to our original problem. And then, now how do we do this? we will do this using the method of a moving frame. Okay, so that's how it's gonna be done. And so now, before we can actually tackle this problem, we would need to talk a little bit about moving frames, remind the definition, and also see some properties of moving frames. Okay, so that's what we will do now. So our starting point is we have a group G which acts on the discrete jet space. So this is just like a group G which acts on a collection of points. Okay, think about it like that. And now, whenever we have this, we can define a moving frame. So here, moving frame will be a G equivariant map, which will go from the discrete jet space into the group. And a G equivariance means that if you evaluate your moving frame, not at a point Z and K, but at G of Z and K, then the answer will be equal to rho evaluated at Z and K times G inverse. Okay. And so here, like the products are different. So inside these parentheses, this is the group action. G acts on points. Okay, so this is the group action inside here. And then on the right-hand side, this is the group product, because rho is a map from the discrete jet space into the group. And so here, rho of this, like rho of n, this is a group element, and then G inverse is a group element, so that's inside the group. There's two different.
What's the sub n for?
Sub n is just a, so the thing is that technically, so whenever you have a function that depends on n, I'll put it as a subscript. So when we construct this.
So there's no relation between sub rows
So-
of n and then rows of m.
Usually it's like, so the function rho can be, could be a function of n also.
Right, but there's no relation between when you change n to m. The two
No.
rows. See your equation row there?
Yeah,
The upper one,
here.
should have sub n on row and on j, right?
J, but that's it. The discrete jet space is like for
It's the
each,
union of all.
is the union of all, and then if you, at a given n, like, so here, the thing is that this is not being being evaluated at a given point. So I'm writing explicitly, like, technically I should have rho, which can be a function of n. Instead, like, technically, like,
Do you want
rho.
it for all n?
So, like, technically, I guess I should write rho usually can be a function of n, and then also, like, z and k, I guess. And this is just, this just denotes z n plus 1, z n plus 2, like that. So this is just a notation to collect neighboring points together, and so now here n can vary. So and so this rho will be a function as n changes. The value of this function will vary. Is that-
Okay. Right.
And just to understand, so a simple example is something that you wrote on the board. Is it what you? So to illustrate this definition, could you illustrate this definition using a simple example?
Illustrate the equivariance.
Just the definition of how.
How to construct a moving frame. Why is it equivariant?
Some useful example of this.
Useful example. So I mean, so
I think
so for
Is that that's why you wrote?
moving frame.
so I will do an example. I will show you pictures of how actually moving frames, like where the equivariance comes into play. So I will do that. So at the end of the day, what's important is I think what is a moving frame. So if you have a Lie group that acts on a space, okay, like here it's the discrete jet space, but technically it could be the jet space, it could be anything. So you have a Lie group that acts on a given space. If you have that, then you can define a moving frame. Okay, then a moving frame will be a G equivariant map from your space where the Lie group acts into the Lie group itself. So this here could be, if you have a Lie group acting on a manifold, a moving frame will just be a map from the manifold into the group, which is G equivariant. Okay, so we could replace this by many different by arbitrary manifold technique. But yeah, I will explain this definition. Okay? So it's not obvious why things work like that. Okay? And so in order to construct like this map here, rho, what we need to do is we need to introduce like what we would call a discrete cross section. Okay, so that's what I would like to talk about. And then once we have this notion of discrete cross section, I will show you how moving frames are constructed and why they are indeed G equivariant. Okay, so here we have our discrete jet space, and then here are these pictures. So it depends on n. It's a U. And so if we start fixing n, we have like a subspace here, and then if we move n to n plus 1, we have a different subspace there. And so inside, so K will be we will call it a cross section of the discrete jet space if the restriction to a fixed index n, so in this, we would now be in this picture here. So K needs to form a submanifold of essentially the fiber over n, which is transverse and of complementary dimension to the group orbits. Okay, so the thing is that n is like an integer. Yes, it is an integer. And so if we fix a given n, now the picture becomes just like the fiber over a fixed n is a manifold. And then we can talk about what is a cross section in that setting. And then it's just the standard definition of a cross section relative to the orbits. And then we can construct a moving frame provided we make two assumptions on the group action. It needs to be regular and free. Okay, so what do we mean by regular action? It means the following one. So if you choose a point inside your discrete jet space, you will always be able to find a small neighborhood such that the intersection of the orbits with that neighborhood will give you connected subset. Okay, so what we're trying to do is we're trying to avoid like having some type of irrational flow on a torus. So we want to have nice orbits. Okay, so that's why we want the action to be regular. And then we want the action to be free, which means that the only group transformation that fixes the point is the identity. Okay? So that's what we require. And then if we assume that the action is regular and free, and we have a cross section K, then the moving frame at a given point Z and K will be the unique group element which will send Zn onto our cross section. That is how the moving frame is being constructed. And so let's see how it works in an example. So say you have a group. Okay, so you have a group which acts on the discrete jet space. You fix, say, n, then you have these orbits. So like the group acts, and then it creates these orbits. Then you choose a cross section to these orbits, which here is denoted in red. So you have this. Okay, so you have these orbits. You have the cross section here. Then you choose a point in your space. Here I have like z. So I'm using z equals like our discrete point. It just makes the picture nicer. Okay, so you choose a point on a given orbit, and then you ask yourself, what is the group transformation that will send z onto the cross section? Okay, and this is what we call the moving frame, rho. Okay? So the group transformation that sends z onto the cross section, this is our moving frame, and it is well defined, provided we assume that the action is free. So if it's free, it's unique, this group transformation. Okay, and then we can verify does such a map satisfy the G equivariance property. Okay, so what we do now is we consider the point G of Z. So we act on Z by an arbitrary group transformation. So this will send us to GZ. And then, by definition, the moving frame at the point GZ will be the unique group transformation that will send this point GZ back onto the cross-section.
Could you explain the definition of regular one more time? Because I didn't think I understood.
Yes. So you have we have like a space, and then we have a group which acts on it. So it will foliate the space, and now we. Like the action to be regular is a constraint on the foliation of our space, and so intuitively what's happening is that so you choose a point, and then you have these orbits near the point, and to be regular means that you can find a small enough neighborhood such that if you look at the intersection of the orbits and the neighborhood, each orbit will be connected. So what's happening is that we're trying to avoid the case where somehow, where two of these curves would actually be the same orbit. And so it's like if you have the irrational flow on the torus, what would happen is say this orbit here would like swirl around the torus and would come back, say, to the one above. And so now, if these two curves are the same orbit, the intersection of the same orbit with this open set would be disconnected, and we don't want that to happen.
Okay.
Yes?
Is the action of the group transitive always?
Transitive? No. So transitive meaning that every 2 points can be
right.
No. So you could a simple. We could just have, say, in the plane we could look at it. We could have just, let's say, translation like that, and so that would not be transitive. We would only be able to connect 2 points that are on a horizontal line. Yes. So we don't require transitivity. If it were transitive, then I guess we would always only have one orbit. And so yes, so we're not making this assumption that, and then
You wouldn't have regular.
yes, and so
No, it's just one orbit, just one line there.
yeah, so that would
One line is
be
always regular, it's always regular.
Okay, well, I'm thinking the irrational form.
Oh, okay.
Yeah. But you're,
no, yes, there can be, it doesn't have to be. And then I would say if it were transitive, then it's not interesting. That's like the interesting cases come when it's non-transitive. Oh yeah, and so coming back to the G equivariant, so like the group transformation that sends GZ onto the cross section, like this group element here, which is this upper arrow here. Now we see that there's two ways to go from this point onto the cross section, either using the top arrow or looking at the arrows below. So you can go from GZ, you act on this point by G inverse, and then you're here times rho of Z, and so you have this equality here. So that defines a moving frame. Or at least it satisfies the G equivariance property. And so we can now do like an explicit computation, say. So we have our group action here, which preserves the finite difference equation, which is written here. So we have this finite difference equation, okay, which has a symmetry group. Okay, so we have, which is written at the top here. And so we have a group action. We can ask ourselves, like, can we construct a moving frame? The answer is yes. And so now, for the sake of illustrating the computation, inside this group action, I chose A and B to be 0, which is a case we've already considered. Okay, so in that case, it makes the whole action very simple. So it's just translation in x and y by epsilon. And so the orbits now are lines. And so we've got these orbits they are lines. So in order to construct a moving frame, we need to choose a cross section to these lines. Okay? And so obviously the choice of the cross section is not unique. And so we choose the one which will make the computation as simple as possible. And so an example, we can arrive and say we'll set xn to be equal to 0. So we're choosing the cross section which is given by essentially the y-axis. And then once we've chose our cross section, we take a point inside here the plane. And now we're asking ourselves, what is the group transformation that will send the x coordinate to 0? Yeah? And so this will give us what we call the normalization equation. We're asking ourselves, by what group transformation should we act on xn so that the output is 0? We're trying to send xn to 0. And now this is an algebraic equation for the group parameter epsilon. So we can now solve this equation. And so we obtain epsilon equals negative xn. And so this expression here is our moving frame. So
And in situations in which algebraic equations are complicated,
yes.
how to go about that?
then we cannot solve them. That is a problem. Yes. It's like we cannot solve everything, but yes. But what is kind of, I would say that what is remarkable is that in many applications it's actually solvable. So yes, it's not. There's no guarantee that you can solve those equations. And also, if you don't choose a nice cross section, the computations can become complicated. And so there's frequently like an art to whatever one is doing. And I would say that if you're like computing moving frames, the art comes into choosing the cross section correct in such a way that will make all your computation easier to solve, or at least.
So this is not yet an algorithm, there is a human interaction. Yeah.
Oh yeah.
Okay.
So there is a human
So
interaction.
that's why it's a new paper, because it's not just you run an algorithm on the computer.
Yeah, okay, so I guess it depends how loosely one wants to be when he says algorithm, though there are like steps to do, like, so, if you want to construct a moving frame, step number 1, like, choose a cross section, so I don't know.
Choose a researcher that can do that. And
Yes, but that's what we mean by kind of algorithm, though, choose a cross section, but that cannot really be done, like, you need like the human assistance, like you said, to choose that cross section. Once you have this, you solve the corresponding normalization equation. And so this procedure is actually implemented in Maple. And the thing, but like you said, but then if you so in Maple, you'll need to somehow like include the group action, and then you'll need to also give it the cross section. But then everything else is done by the computer. Yes, because one needs to specify the
So you try one cross section, if it doesn't work out right, then you try
another one. Yes. Technically, it should work. Like if the cross section is transverse and the group is free and regular, then the moving frame, you have existence of the moving frame, but it doesn't mean that you'll be able to solve the equation. And so if you're not able to solve them, then you try to choose a different cross section.
Is it actually necessary to solve equations, or you can just leave it in the form of?
The thing is that it's true that for what we're doing and for the problem of solving finite difference equations using moving frames, you don't even need to know the moving frame is. So you don't need to solve the equation. Okay. So you only need to solve the equation if you want to have coordinate expressions for the moving frame. But you don't, in many problems, you don't need that. In fact, you just need to know the existence of such a map. Yes, there are, yes. So that's Peter, has obtained many results in the recent years just by using the machinery of moving frame, where the existence was just good enough to prove these existence results. And you need to know the moving frame explicitly if you want to have explicit formulas. In general, you can do a lot without knowing those.
Is the regularity more a problem of your cross-section or of the orbits?
I would say of the orbit.
Of the orbit.
Yes. Yes. Yeah, yes. You need the orbits to be regular in order to be able to uniquely specify your cross section. So you need the regularity to be able to define rho uniquely, like. So it has nothing to do with the cross section.
So how do you test whether something
Is regular?
is regular?
I mean, in practice, to be honest, you don't test anything. You give yourself a group action, and then you're like in practice you look at it, and then you sort of look at the first two equations, and then your goal is to solve for epsilon. That's it. Like. Because to construct a moving frame, you need to be able to specify epsilon in terms of x and here y, and then so you're like so here the.
But that's for this translation group. What about some other groups?
Oh yeah, but even then, if I were given a group action, I would say, oh, I'm trying to solve for the group parameters. I will try to set things to the constant and hope that I can solve it. In practice, that's what people do. Like, you can, but.
So the change in x coordinate,
Yes.
from little xn to capital Xn,
Yes.
in other words, what you call epsilon,
Yes.
would it always just be dependent on the x coordinate and not
No,
on the y as
It
well?
can be
On the y.
dependent.
For example, if
on
I take a cross section which is perpendicular to the orbits.
But the group action would still be like that.
Yeah.
You would change the, yeah, so yeah, there's no, there you could totally take a cross section like this. Yes, definitely. And so, so that would be, so in that case, like, I guess, I mean,
No,
one could take the,
Don't
you
worry.
would have, say, you would have like y equals negative x. I think that would be perpendicular to these lines. And then now you would want to send a point which is on this equation, on this line, so you would have capital Y equals negative x, and then you would take the formulas for capital Y, capital X, plug it inside here, it would give you now an equation for epsilon.
Okay.
And I agree that if A, so the thing is that in this case you would have negative x plus epsilon on the right, and then the y you would have this big expression here. And now you would need to solve for epsilon. And so you would have an epsilon on the right, an epsilon on the left, and then the epsilon on this one is raised to possibly a power, and then it becomes a little bit more complicated to solve. And so that's an example where geometrically it seems to make sense to want to maybe have a cross-section which is perpendicular to the orbits, but if you actually want to solve for the moving frame, that is not something you would want to do. It leads to an algebraic equation which is actually difficult to solve. Yes. And so once we have a moving frame, we have this procedure which is called invariantization, which creates invariants. Okay, so this is very systematic. So you're given your moving frame, which we'll just now denote by rho n. I won't write its dependency anymore. And so if you give yourself a point Zn, you can invariantize that point. And so that's denoted by iota of n of Zn. So we're invariantizing Zn. And how do we do that? Well, we just act on Z by your moving frame rho. Okay, so and then the claim is that the expression on the right is invariant. So it doesn't change under the group action. Okay? And we can verify this. And so we can verify that it is indeed invariant. So we can act on the invariantization by an arbitrary group element. Okay, so we do the action. So we then write the definition of the invariantization is just rho acting on Z. But then because we're acting by an arbitrary group element, we replace, we then act on every occurrence of Z by G. We have this expression. And then we use the G equivariance of our moving frame to pull out the g which is inside the parentheses, so we have this expression. And then here now g and g inverse cancel each other, and so that shows that this quantity, the inversionization of Zn, is an invariant. So once we have a moving frame, we can construct invariants in a very systematic fashion by invariantizing. And so here's an example. I mean, it's always the same one. So you have here I wrote the group action. You have this. Okay. And now we also have a moving frame. So at the moving frame, we wrote that now it's written here. So in the previous slide, we constructed the moving frame. We know that it's given by setting the group parameter equal to negative xn. Okay, so let's say you want to invariantize the x coordinate of a point z. Okay, so you want to invariantize x of n plus 1. So we know how to do that. You act on the variable by the group element. So the action on x is just translation by epsilon. Okay, so xn plus 1 becomes xn plus 1 plus epsilon. And then now we want to act not by an arbitrary group transformation, we want to act by the moving frame, okay, where epsilon is equal to negative xn. And so we replace epsilon by negative xn, and we obtain this difference xn plus 1 minus xn. And so now the claim is that this is indeed an invariant, which it is the case because the action on x is just adding epsilon. So if we add epsilon to xn plus 1, we have plus epsilon, and then if we add epsilon to xn, we have plus epsilon, but there's a minus sign in between the two, and so they cancel. That creates an invariant. Then we can also invariantize like y coordinates. So if we invariantize this ratio, if we do the computation, we obtain this expression. And then one could verify that this expression is indeed invariant under the group action. And I'll denote that by Jn because it will come into play. And then we can, I guess, do that in general. So for the next couple of slides, the invariantization of the point Zn by iota of n, or like the invariantization of Zn, I'll denote that by capital In. And then we can also invariantize the discrete jet of order k, and then I'll denote that by capital IKN. Okay. Just some notation. And then usually these invariants are called normalized invariants. That's just terminology, so you can, that's how they're called. The key is that the expressions that you obtain are all invariants. And so now we can create, in principle, infinitely many invariants. I can just invariantize any points with my invariantization map and create many of them. But it's like useless to have infinitely many invariants. We want to have a finite number of invariants from which we can create all the other ones. And so if we're in differential geometry, usually we use the derivative. We can differentiate invariants and obtain new ones. If we're in the discrete case, the derivative operator is replaced by the shift operator. And so here we have S, the shift operator, which takes n to n plus 1. And so then, once we have this operator, we'll say that a set of invariants generates the algebra of joint invariants, so generates all the invariants. If any invariant can be expressed as a function of the generating invariants plus their shift. Okay, so I don't know, there's let's say 5 invariants in this guy here, so with these 5 invariants plus their shift, we can create all the other invariants. That's the idea. And so the natural question, I guess, is what are the invariants inside the generating set? Can we identify those invariants? The answer is...
But to start with, how do you add and multiply invariants?
How do we... So if I have 2 invariants, I would just take the usual multiplication. So they're functions. So like this is one invariant. So this, like this difference, x, like xn. So one invariant is xn plus 1 minus xn. So this difference is an invariant. And then I could divide or multiply by another invariant, which would be xn plus 2 minus, say, xn. Like the difference between 2x is always an invariant in our example, and so I can take the quotient of two invariant, it will remain an invariant. I can add two invariant and it remains an invariant. So the usual product and the usual sum. Yes. And so now, like I said, the question is, what is included, what do we need to include inside our generating set to make sure that we can generate all the invariants?
And it's algebra over real numbers. Is that what we're
The algebra over the real numbers. And so one of the some of the invariants that will be included in that set are called Moore-Cartan invariants. So if you're given a moving frame rho n, you can compute this product. So rho n times rho n plus 1 inverse. So this is inside the group, but the output is an invariant function. So if you compute that, this is invariant. And why is it invariant? This comes from the G equivariance of our moving frame. Okay, so if you if you act on this quantity Mn by a group element, okay, then you write the definition of Mn, and then you act on it with an element G, and then you use the G equivariance of rho, and rho n plus 1, and then the G's cancel here, and you recover your expression Mn, which we call the Moore-Cartan invariant. Okay. The reason why they're called Moore-Cartan invariants is that they have something to do with so Peter over at some point introduced what are called the Moore-Cartan invariants in the differential case, which comes from pulling back the Moore-Cartan forms that we know when we have a Lie group. And so these invariants are related to those ones in the discrete case. And so the proposition is the following one. So the order 0 normalized invariants, so the ones that you obtain by invariantizing Zn, and the Moore-Cartan invariants, they generate the algebra of finite difference, the algebra of joint invariants. Okay? So if you know those invariants, then you can construct all of them from those. And then this can be proven using the recurrence relations that exists. And in the finite difference case, we have the following proposition. So if you invariantize a point Zn using iota n, and if you invariantize Zm using iota of n plus 1, these two expressions are invariant, and they're actually related to each other. And they're related as following. So if you invariantize Zm by iota n, it's equal to the Moore-Cartan invariant acting on the invariantization of Zm by iota n plus 1. There's this relation. And it's not difficult to see why that would be the case. You just need to write the definition. So the invariantization of Zm with respect to iota n is just you act on your point by the moving frame rho n. And now what we do is we just introduce the identity element between the two, like this. And then rho n times rho n plus 1 inverse, this is what we call the Moore-Cartan invariant. And then rho n plus 1 acting on Zm is just iota, the invariantization with respect to rho n plus 1, which is this quantity. So it relates these two invariants together. And then one can so one can kind of repeat this recurrence relation, and then one can say that the invariantization of Zn with respect to iota n is related to the invariantization of Zm with respect to iota of n plus k through like a succession of including the Moore-Cartan invariant inside. And so what is key is that if you replace m by n plus k inside the last formula, we obtain this formula. So the invariantization of Zn plus k can always be related to the invariantization of Zn. Okay? And so if you know the invariantization of Zn, you can start shifting that with your operator, and then you act on it by these Moore-Cartan invariants, and then you can express any invariance using the order 0 invariance and the Moore-Cartan invariance. That's the key, I guess, here. So any invariant can be expressed in terms of the Moore-Cartan invariance and the order 0 normalized invariance and their shifts. And so now that we know this, in fact, we can express any invariant function in terms of In and Mn. Okay, the idea is the following one. So if you have any invariant function, like here In, script In, because it's already if it's invariant, then the invariantization of an invariant is just the invariant itself. Okay, so we have this equality, and then if you have this equality, if we write it down, it's the same thing as saying that the invariant In is equal to its invariantization, which is here. But now we just saw that the invariantization of any point, Zn plus k, or in general the invariantization of jet, Zn k, we can always express these quantities in terms of m and n, mn and in. So these invariants that we have here, we can always rewrite them in terms of these guys. So in other words, any invariant can be written in terms of the Moore-Cartan invariance and the normalized invariance. Yeah, so if we come back to our running example, so we have the moving frame, which is epsilon n equals negative xn. Then we can compute the Moore-Cartan invariant. And so it's rho n times rho n plus 1 inverse. And now, this is usually the group product. In our case, it's just addition. And so the inverse is just negation. So this product becomes epsilon n minus epsilon n plus 1. And then epsilon n is negative xn. And so epsilon n plus 1 will be negative xn plus 1. The minus cancel, and we obtain this quantity, which is invariant. And then here I'm just recalling. So then we can start invariantizing, say, xn and yn plus 1. The answer is these quantities, which we've already done. And then we can look at the recurrence relations, for example. And so if we say invariantize xn plus 1, the recurrence relation says that this is equal to shifting the invariantization of xn. So in our case, the invariantization of xn is just 0. So if we shift 0, we have 0. And then we act on 0 with the Moore-Cartan invariant, which is just here, mn. And so the invariantization of xn plus 1 is just the Moore-Cartan invariant. And then we can continue to do that. So if we invariantize this ratio, apply the recurrence relation, we can show that this invariant can be expressed as equal to jn plus 1 minus this ratio. Okay? So this can be done technically. The key is that we could continue to do that, and we could express the invariantization of any quantity in terms of mn and jn. So with this, we can now come back to the problem that we wanted to solve, which is how to solve a finite difference equation using the group foliation method. So we can look at that. So there are 3 steps. Step 1, project the solution space project all the solution onto the space of invariance, solve the problem in the space of invariance, and then reconstruct the solution. And so the projection goes as follows. So we have a finite difference equation that admits a symmetry group G. Okay, so the first step is you want to construct a moving frame. So you have a group, you can construct the moving frame. So you construct the moving frame. And then, because we're assuming that the equation is invariant, we can invariantize this equation. Okay, so we take our equation, because it's invariant, we can invariantize that equation, and then we can write all the equation in terms of these normalized invariant I and k. Then you can use the recurrence relations to re-express the result in terms of the generating invariance, so the Moore-Cartan invariance and the order 0 normalized invariance. And then we obtain what we call the resolving system, which is the original equation projected inside the space of invariance. Okay, so that's the projection step. So you construct a moving frame, you invariantize, and you obtain this equation here. And so for like for the problem that we're looking at, so we have this. This is like the finite difference equation. Now we invariantize this. Invariantize this. These two equations, and then in the space of invariance, these two equations reduce to these two equations. So on the right-hand side, like xn plus 1 minus xn, that is indeed our Moore-Cartan invariant for that problem. So this Moore-Cartan invariant has to be equal to h, and then the Moore-Cartan invariant appears here also, so that's why we have mn. And then each of these two parentheses, the first one on the right, this is just Jn, and then the second one, this is just Jn shifted by 1. So we have this finite difference equation. Then step number 2, you want to solve the system that you've obtained, like in the space of invariance. So you can solve that. And so for us, this is just a linear finite, first order linear finite difference equation, which can be solved, and then Jn will be given by this formula. So here J0 is a constant, and so that's the solution. So we've solved the problem inside the space of finite difference invariance. The next step is to try to reconstruct the original solution. And so go from the solution inside the space of invariant back to the original solution. And so this will be done by considering what we call the reconstruction equation. So given a moving frame rho n, we can look at its inverse. Okay? And we will call this rho n bar. And rho n bar satisfies this very simple finite difference equation. Okay, so rho n plus 1 bar equals rho n times the Moore-Cartan invariant rho n. So we have this equation, and this could be just proven by writing what rho n bar is and writing explicitly what the Moore-Cartan invariant is. And so if we can solve this equation, then we can actually recover the original solution. Why is that? Well, by assumption we would know what In is, and then by definition In is just the invariantization of Zn, which is just rho n applied to Zn. So if we multiply this equation by rho n inverse, then we obtain Zn is rho n inverse acting on In, which is just rho bar acting on In. Okay, so, and then the solution we're trying to find is Zn. And so if now we know In, if we can solve the reconstruction equation, we'll know what rho n bar is. We compute this group product, or this group action, I should say, and then we recover the solution. And so in our example, we found that we know that the Moore-Cartan invariant is constant. It's equal to the step size h. We have the reconstruction equation, which is here, and then rho n plus 1 bar will be replaced by rho n plus 1 epsilon n plus 1 bar. And now here, this is the product inside the group, and now the product is just the sum. So we have this equation here, which we can then solve for epsilon n bar. So we solve that, and then epsilon n bar is given by this expression here. And then we know that the invariantization of xn is 0, the invariantization of yn is this expression here. And so we can act on this by our by our, I guess our moving frame, then the inverse of the moving frame, rho n bar, so we do that. So if we act on 0 by rho n bar, we'll obtain xn, which is this expression here. And then if we act on the inversion of yn by rho n bar, we will obtain yn. We do the computation, and then we obtain this formula here. And then this gives us the solution to the original finite difference equation.
From that formula for the solution,
Yeah.
can we guess what the solution of the differential equation was? No, really not. William thinks no.
They were just points.
Huh?
You just get points on it.
Yeah,
Well,
so,
but is it? Could you?
so this will solve the.
Numerically.
So this will solve the. So this will solve the. This will solve the finite difference equation. So then you have. So there's no reason why, like, if the finite difference equation is not exact, it's like there can be an error, and so it might not tell you anything about the solution to the differential equation. It can only tell you something if you somehow knew that the finite difference equation was an exact approximation of the differential equation.
but what happens if you plug this in?
Plug this inside the
Differential equation.
differential.
It's not going to be. It's not.
No, no.
I don't. So the truth is I don't know because I haven't tried though. But like I would need to try and see what happens.
Okay.
Yes.
Okay.
So no. So like in general, like the solution that you obtain will only be an approximation of the actual solution to the differential equation. Because the finite difference equation is only an approximation of the differential equation.
So how well does this thing converge to a solution in some sense? I mean, is it well conditioned or?
Yeah. So I mean, this was not the. I guess that was not the purpose of this like computation or.
It's not to provide a numerical solution.
No. So I think like this computation, one should take it as like something as finite difference equations are allowed to exist on their own.
Of course.
And
I see.
no, but so if one from that perspective, then one does not have to ask himself like these convergence questions because one could just be interested at I want to solve these equations. Can I do it? Yes, and then. But then I would need to develop, like we want to develop tools for solving these equations, yes. So, but it's true that if they are indeed the approximation of a differential equation, after that one can ask himself, is that a good approximation? Is that not a good approximation?
Why not use Euler's method? Just or
but that is a totally different problem. So yes, but that was not. I guess that was not the goal here. Like it's more. Here's a finite difference equation. So you don't know, you're doing a problem, and then you're like, oh man, I got to solve this problem. How do I do this? So, like, then one could search for symmetries, and then it's like you can start it. I'll try to see if that equation has symmetries, and then say, oh, it has symmetries. Now that I have these symmetries, I'll try to use those to my advantage, and then solve the equation. That's a problem that could occur.
And the original differential equation with A and B, for all sorts of values A and B, is it good for modeling something? Where does it come from? Or was it an artificial example?
I think it was more for like a toy example.
Toy example.
Yes. So it's it's an equation that has like symmetries, which is not too complicated, and whose finite difference approximation is not too trivial, and like mix of to try to illustrate the construction. Like so if you take symmetry groups that are too simple, then the standard approximation, finite difference approximation will work. and then these ones tend to be straightforward to solve without using any like advanced group techniques and stuff. So, no, I think it's more to try to illustrate the procedure more than being important in application.
Well, I mean, Peter Ober showed some example using this kind of method, where the other method just don't work, right? Or not work well.
But it depends what you mean by example, but probably yeah,
I mean, applications, actually,
Yeah.
actually, you know, like solving a jigsaw puzzle.
sure. Yeah.
Okay.
Yeah. So I'll just end by making, I guess, one comment because I'm way over time. I just want to emphasize, emphasize the following. So, like in this presentation, I was giving you like all the explicit formulas for the moving frame, all the explicit formulas for the invariance, all the explicit formulas for the Moore-Cartan invariance, and it makes like the thing is that in order to actually use group theory to solve these finite difference equations, you don't need these formulas. So there's like in principle to implement the group foliation method, you don't need to know what rho is, you don't need to know what ion is, you don't need to know what the Moore-Cartan invariance is. If you go through all the details, you realize that you just need to know that they exist. Okay, and so in particular, you don't have to ask like to worry if you can solve the algebraic equation. Okay, so that's good. You just need to know that they exist, and if you have this, then you're actually able to the existence. You can actually implement the whole procedure. The only thing you need to know is the group action, so like the symmetry group, the choice of a cross section. So you just need to know that it exists. You just need to know that this one will work, even if you don't. And then you need to know the recurrence relation. Okay, so that's how it relates the invariants. And you can write down the recurrence relation without even knowing what the invariants are. So it just tells you this invariance is related to that one in that form, and you don't really care about their their coordinate formulas.
So what kind, so, I mean, if you are given a difference equation,
Yes.
right?
Mhm.
So that's your recurrent relation.
Yes. Yes.
How do you know whether there is a legal action on it?
Yeah, so that you could do it like using the. I don't know how familiar you are with like Peter's books, like symmetries. I don't know if you. So maybe you know how to compute symmetries of differential equations.
No, I'm talking about just difference, I mean.
Yeah, no, but so I would say
Would the difference.
it's very
Galois
similar.
group-
So
Would the different Galois group be involved, for example?
no.
It's not
No,
linear
it-
equations.
Huh?
No linear equations.
No, it's true that so you wouldn't be able to do the Galois stuff, but
I mean,
you
I could give you linear difference equation.
yeah, then you would be able to. But what you can, so there are all these like algorithms to compute symmetries of differential equations, and they're all implemented in Mathematica, Maple, Maxima, and all that stuff. You can adapt these algorithms to give you these symmetries of finite difference equations, and after that we should put those into a computer eventually. So that I would say is like, yeah, can be done. That would be in fact step number 1. You're given an
Yeah, right,
equation,
right.
find the symmetries, yes. And that can be done the same way as you would do for differential equations. Thank you very much.
Huh?